Did we start 7.4 in class last time? The last set of rules? I don't think we did we?
We did, like the exploitation material equivalence rules last time.
Okay, cool. Yeah, we're running out of time. I thought I could cram all this in pretty quickly. And it's taking longer than I thought. Okay, yeah, okay, so we did do it. How are you 3 or 4? I didn't see you come in. How are you guys feeling about 7.3, 7.4? Are the proofs okay?
I had a couple questions that I couldn't figure out in 7.4.
Yeah. Okay. Yeah. Let's look at it. Let's start class by looking at a few of those. I'm hearing my own voice is bugging me, so I'm gonna fiddle with this now. How about computer? Okay. So 7 questions from 7.4. Which problems in particular?
It was 6 and 24.
6 and 24. Oh, come on, is there some kind of feedback? All class. Okay, 6 and 24. 7.4.3.
Yeah.
Is it the same for you, number 6? Okay, cool. All right, so walk us through what you have already until you got stuck.
I think I just didn't really know. Let me find it again. Like I saw things that I could do, but I just felt like I couldn't actually get to the F to J. Like I felt like every time I tried to turn it around, I just kept getting like stuck.
Okay.
So I tried to do like a hypothetical syllogism, and then I think later I tried to do the one where you deny the antecedent, and you get the or, and then the consequent, but.
Okay, cool. So let's do a hypothetical syllogism. So that will get us F then B then J, right? From 1 to hypothetical syllogism. Man, this chalkboard is so clean and nice. Okay, so then did you do anything after that?
I don't know, my notes are kind of. And then I tried to do F and B to J, like the
Exportation? Yeah. Okay, so exportation is this rule. If you have P and Q, then R, that's the same thing as P, then Q, then R. Right, that's exportation. Correct? Yeah. So, okay, so then we would end up, if we used exportation on 3, we would end up getting F and B, then J. anything after that? Is that
It
weird?
went downhill from there.
Yeah,
It's just-
okay. So let's look. I mean, I don't know how to solve it off the top of my head. Let's figure it out. Does anybody see what we could do for this one?
I did the exploitation on number 2, or on line 2, so it was like B and B to J.
Okay. So B and B to J, Q exploitation. And what's that allow you to do?
With the tautology, it's just B to J.
Yeah, with the tautology, just ends up being B to J. Right, because B and B is the same thing as B, right?
I knew I was missing something.
Yeah, I didn't see this either until someone did this part. Just did this, and I was like, oh, yeah, okay.
I got it now. It's
Yeah.
all good.
So we got B to J, and then we just finish it out by doing hypothetical syllogism on 1 and 6, right? 1, 6, hypothetical syllogism, F to B, B to J, therefore, F to J, truth, valid, yeah. Got one little thing, right? Yeah, but I didn't see it either. Okay, any questions on this one? Is my voice clear? Is it echoey? Sounds echoey to me. I guess it's just because I hear myself talking twice. Okay. Did you have another one?
Yeah, I had 24 too.
24. That's Ivan E, right?
Yeah.
Let's see. C will not see. Therefore, I. Okay, where'd you get with this one?
I feel like I'm probably doing the same thing I did on 6, where I'm just not seeing it. But I think I tried to do implication for the first step with number 2, so that I could get not C through tautology.
We would do 2 implications. And we do, so it would be not C or not C, right?
Yeah.
And then you want to do a tautology, which would just get you not C. Because if these are your 2 options, then it's going to be not C, right? If one of those has to be true, because it's the same thing twice.
I think I just solved it.
Okay, so we got not C, and then what'd you do from there?
I didn't do it, but I think, can you get not I then E?
Get
Yeah.
not.
Yep.
I then E from 1 for modus tollens, 6.
And then can you do, shoot, what is it? Is it implication where you can do not I or E, like the,
Like this?
yeah,
Yeah.
yeah, and then,
5 implications.
yeah. And then you can do the Mormons.
The Morgan, so I'm gonna, again, you can think about distributing or adding. When I add one to the outside, it's gonna make it positive. Add one to the inside, that becomes positive. Flip that becomes negative. I and not E. 6 to Morgans. 8.
You can just
And
get
then-
I.
Good, let me just simplify the I.
I
Yeah.
don't know what I was trying to do.
Sometimes you just, until you get there. It's like when you go to a mechanic and you're like, my car's been making a noise, and then it just doesn't do it, and that's the mechanic. So, all right. Any questions? Any other problems we want to go over? Anybody got anything? So, okay, I want to teach you, and like I said a few times, it's kind of hard to know how much time to devote to each of these parts, because some people are still not super comfortable with the rules, but they're comfortable with doing proofs in general. Some people are comfortable with both. We're running at different speeds, so I don't want to introduce too much new stuff, but we are running out of time. The test number 4 unlocks today, which is all of these 18 rules, 7.1 through 7.4. And I would really like to, even though I don't understand exactly why this is the case, even though the department and a lot of people don't think you need to know this, there are 2 additional techniques for doing proofs that don't involve rules, but they're techniques that if you do something like math, or if you do serious philosophy and start looking at some arguments from before the 19th century, you're going to need these techniques to do it well. And what the techniques are is they are 2 different ways of making assumptions of, well, what if, given these premises, what if something else was true? And so you can assume whatever you want, right? So let's say I have, this is called conditional proof. But the problem is to master these techniques, it's definitely going to take more than a week. And I have basically truncated my ability to practice this and teach this to you in 1 day each. So this week is all we have. And it's part of the homework, but I won't test you on it. But again, like, it is, like, this is actually, I think, one of the most important parts of the textbook. But because I also have to teach you a whole new language of logic starting next week, I don't have time to spend as much time as I'd like, if that makes sense. So you'll have to kind of practice it a lot on your own to do that homework. But okay, so looking at, I believe it's 7.5. 7.5 covers this technique, and all you really do, let's say I have P then Q, let's say I have P then Q, Q then R, I have H then T, now H then T or not T, and then we're going to do this not P, not P, therefore R. Okay. So in this argument, you can solve this with the rules we currently have, right? But there's another way to solve it. And what I can do to kind of, instead of having to use hypothetical syllogisms a lot, instead of having to play around with doing De Morgans and negating the right-hand side here or something, I can just make an assumption. And what I'm going to do, this is how I write it at least, I'm going to like drop down here, I'm going to indent a line. I'm going to go 6. I'd like to put a little bracket here. I'm going to put assumed for conditional proof. What is a conditional?
If the condition is met, then it could happen.
Right, if this condition, the sufficient condition is met, then that's going to happen. Another way you can say is it's hypothetical in that if this happens, then this happens. So what we're doing with the conditional proof is we're assuming that something is true. We assume something for conditional proof. We draw out the implications of it, what the premise is, and then we close our conditional proof and say, well, let's just say I assume that H was true. We don't have that anywhere here, right? But we can assume it. If H was true, what would that mean? Well, if this was true, then it would imply T or not P, right? From 6-4 modus ponens. 8. Well, given this assumption, I've gotten this, and given this, and 5, I can get T, right? So I could say 5, 7, disjunctive syllogism. Now that's all I wanted to do with this assumption. I made an assumption, and I saw that given the premises and our rules and this assumption, I was able to derive P. Now it's an assumption, right? It's not true. It's just an assumption. So I close this out, and I now come back here, 9, and I say, well, because I made this assumption and showed you how it implies this, it must be true that H implies P. And then you can just say 6 through 8 conditional proof. Does that make sense? So you're making an assumption, you're drawing out its implications, and then you're kind of finishing up and saying, here's how this assumption gets me here. So if this assumption was true, then T would be true. And then I just represent that here. Is that questions on the general technique? Okay, then I just finish out the proof like a normal proof, right? I have H then P. Could we actually solve this? P. No, this would be invalid. But I can get close, right? I can go H then P, I can do hypothetical syllogisms, and eventually I'll get to H then R. Or just say a bunch of hypothetical syllogisms combined, and then I would need something else to get R, right? I would need a positive H, but I don't have that. Now I could assume an H, but it's still just going to result in a conditional. So I just kind of fucked up the problem. But let's say the conclusion was H then R, then that's how you would solve it. Now you could do that with the rules, right? In a straightforward way. Or you can make assumptions and see what those assumptions would entail. And that gives you this conditional. Questions? Okay, let's look at some of them in the book. The reason why this is important is because there are certain kinds of arguments that you can't really actually use the rules to prove. Or if you can, it's going to be extremely complicated and tedious, and it's going to take a long time. And this saves time, but there are some types of arguments that it's just absolutely necessary for. Have you guys ever heard of a reductio ad absurdum? So a reductio ad absurdum. It's a reduction to absurdity. And what a reductio does, is just a type of argument, is it says, okay, I'm going to show you why your position is wrong. Because if your position was true, it would entail a contradiction, or it would entail something absurd, right? A contradiction is an absurdity, right? So the form of a reductio is that you start out maybe with some premises that are true, and then you assume some position, right? You assume, let's say, your gun control argument. The two ways I can argue against your gun control argument is I could defeat your argument, right? But I can also take your conclusion and show that it results in a contradiction. And now I'm not just undercutting your argument, I'm actually defeating your position, right? So I have some premises, and then I assume your conclusion. Let's just say we need gun control or something like that. I derive a bunch of stuff from that. I end up getting a conditional, let's say G then P. But somewhere up here in the premises, I already know that not P. So then I know your position is false, not G. That's what a reductio is in its normal form. It's again, if we were going to, they're notoriously, the actual reductios you read in philosophical or theological texts are notoriously difficult to put into symbolic logic and standard argument form, unless you have conditional proof. And reductio was the most common way of arguing for more speculative topics, like the existence of God, or in metaethics, you have things like certain theories about what morality is. you can't really argue with direct evidence against those. You have to take the position and unpack what it would imply, assume that it's true, and then see if you could find a contradiction in there somewhere, right? So basically our entire symbolic logic system wasn't even able to model this kind of argument until we get this technique. Does that make sense? Why it's important? Okay, I'm just going to start out by doing this one. So you can see T or S. Wait, am I right? Yeah. T or S then K. Therefore, G is K. Okay. Has anybody started this chapter yet, 7.5? Okay. Kind of? Who is it? Oh, no, yeah, okay. That's fine. I mean, I don't care. Given the technique I just showed you, do you see an assumption we could make that would help us get to here? And again, you can make up whatever you want. You can assume anything you want.
You could say T then T or S.
It would be T then what?
T then parentheses T or S. And
So
then
it's the same conditional proof for.
then you could just connect it all with hypothetical solutions.
Okay, cool. So if we assume this is true, then what that would mean is, well, we got G and T, so we go 1, 3, hypothetical syllogism, and we end up getting G then T or S, right? Well, we know that T or S implies K, so we'll get 2, 4 hypothetical syllogism, G implies K. Now that's the conclusion, right? But you didn't prove it. What'd you prove?
Nothing.
Well, you proved something. What is it? If this is your assumption and it implied this, then you can say, if this is true, then this is true. So if T then T or S, then G then K. 3 through 5 conditional proof. Do you see how that works?
So this is basically like saying, so a normal math problem is 2 plus 2 equals 4, but this is basically like saying 2 plus 2 might equal 4.
Kind of. It's like saying a normal math problem would be saying 2 plus 2 equals 4. Or it would give you 2 addition, and then you derive directly 4.
Like
This
it's a
is like-
certified answer versus like a possible answer.
Yes, yeah. It's a purely hypothetical answer. Yeah. Does that make sense? Yeah. Okay, so this is what we got, and maybe it's useful, I don't know. But it is purely hypothetical. Can we use this to get to here? Ever see anything we could do? Or another assumption we could make or anything?
Sure, it's a temporal norm. So would you make it to where then now the goal is to prove T then T or S correct?
That would be one way to do it, yeah. How could we do that?
You can make another assumption where you assume G.
Cool. Let's try it. So, can you all see down here? Below? Okay. So I'm going to indent again and start another conditional proof. I'm going to say, assume for conditional proof, you said G?
Yeah.
So let's say I assume G. What does that give me?
That gives you T.
It gives me T from 7-1 modus ponens. Okay?
And then you can do T or S with addition.
We can add here T or S would be 8 addition right? My writing's really bad. 10?
And then you get K.
Good, and then I get K.
Yeah, 9-2 most friends.
9, 2, most ponens.
And then you can get exit the conditional proof and you get G and K.
Good, I close my conditional proof right here. And I now say, my conclusion is, if I assume G was true, then I would get K. And that's the conclusion, right? You see how that works? So this is obviously a very powerful tool because you can make stuff up that's not in the premises. You can basically go, okay, we agree on all of these facts in the premises. Now I'm going to assume one more thing. And I'm going to show you how this assumption, paired with what we already agree on, would get me some conclusion. And that's a very fruitful way to argue, right? Because you're starting from a commonplace. They're just saying, now let's just grant me one more assumption and I'll show you what it would mean, right? That's a typical way of arguing for a lot of stuff. Okay, any questions? All right, let's put another one up here, maybe a harder one. R and B. I keep losing my place. R and B. R then C, then F. B, then F, then H. Therefore, R, then H. Okay. So you got all 18 rules. Also, can you believe we learned 18 rules? That's crazy. We're already done with all 18, the semester's flying by. Okay, so we've got our 18 rules, we've got this, we've got our conditional proof technique. How can I solve it?
You would assume R.
Okay, so let's start my indent here. Let's assume R. What are you going to do with that?
Then you can get B with 4-1 most friends.
B for 1 most ponens.
And then you can also get B and F
Good.
with 4
For 2 most ponens.
And since you have B, then you can also get F and H with 3 most friends.
F and H. 3, 5 most ponens.
And you can also get F because you have B on line 5, so 5, 6 most friends would get you F.
Good. F.
Which means you can also get H with 7, 8 most friends.
7, 8 most ponens.
And then you would close the conditional proof.
Close that. I assumed this, it got me this, so I can say, I just proved that if R happened, then H will also happen, there's the conclusion. Good.
So basically, like when you close it, when you're doing the next line, it has to be the first line and the last line.
Yes, yeah, wherever you close it, your conclusion will be, assumption is the left-hand side, right-hand side is whatever you concluded at the close, yeah. And again, this could be a big string of things. So could this. You can also close it wherever you want. Now, what would happen if I'm not sure what problem to do for this. So I'll show you what's possible. Let's just say I was doing some conditional proof. Let's say I have as a premise P and Q. I don't know what conclusion I'm going for. Let's say I have P and Q, not R. And I want to start my conditional proof here. So let's just say I assume T. Well, let's say R or T. R not T. I assume T, and I derive from that not R, from a disjunctive syllogism on 2, 3. That gets me not R, but that doesn't really get me anything further, right? I'm just kind of stuck there. I don't know, again, what conclusion I'm going for, but I just want to keep using the rules to do something. But I can't really do anything else, can I? I can maybe use conjunction, but I can't infer anything by combining, right? I can't do anything substantial. Well, what I can do is I can make a second assumption. How would I do that? An indent within the indent. I would go 5. Now I'm doing a conditional proof within a conditional proof. So I started with this assumption, I got not R. Now I made another assumption within that assumption. And let's just say I say, here's my assumption. Q implies R. Now, given this assumption, what follows?
Not Q.
Yeah, not Q, good. And that would just be a 4, 5 modus tollens. Now let's say I want to close this. What did this just prove?
Not Q.
It proved not Q, but with this assumption, that's my starting point, that's my closing, right? So what, 4, 5, 6, 7, I close it, I go back to the original proof, conditional proof, and it proved that if I assume Q then R, then I get not Q, right? 5, 6 conditional proof. Well, but that's still within a conditional proof, right? So let's say I close the conditional proof here. And I say 7, 8 to come back out. I like to think of it as coming back out into the real world, where these are like possible situations, right? So I come back out and I conclude now that if I assume T, then if Q then R was true, then not Q would be true. See how that works out? 3 through 7 conditional proof. I just did a conditional proof within a conditional proof. Now the other way to think about it, which with the, what rule is that, exportation? If we did that on here, what would this be with exportation?
T and Q to R.
T and Q to R. Then not Q. Think about what that means. Exportation. It's a long vest to wear with Chuck. What we did with the conditional proof was I basically say, grant me this assumption, T. Now, if I assume T, then I get this. But also grant me another assumption. If I now assume T and Q then R, I will end up getting Q then R, then not Q, right? So if, well, I should say, if I assume this and I assume this, I get not Q, right? If I assume this and I assume this, if these two things happen, then I would get not Q. Does that make sense? So this is basically, like the conditional proof was just a way of proving that this thing was true. Given these two assumptions, this would follow. Purely conditionally or hypothetically. Does that make sense? You can do as many of these within things as you want, right? And in programming languages, conditional proofs are really important because it's setting up a sort of conditional proof, because it's setting up conditions within subconditions, if that makes sense. Okay, questions? Okay. What do you think? Do you want to practice some of these together? Or do you want me to introduce you to the other technique right now? We could practice conditional proof for the rest of the class. And then next time I introduce indirect proof, we practice that. Or I could introduce them both right now. Then we practice both of them next class. What do you think?
Can you do both?
You want me to introduce both? So there's one for both. Do you want that too? Votes? Anyone? Sure. No one really cares. Okay. Indirect proof is very similar. You're still going to make an assumption. But this time, instead of it just being merely hypothetical, what you're going to do is you're going to assume I shouldn't say normally. You're still going to assume something, but you're going to try to assume the opposite of the conclusion. So here's the example the book gives. Again, my iPad is here. This is 7.6. If we have A or B, then C and B. C, then not B. And the conclusion will be C, not A. Sorry, my writing is really bad. Okay, so this argument says, look, if A or B is true, then C and D is true. C would imply not B, therefore not A. What we can do is we can assume that the conclusion is false. Why would we want to do that? Does anybody have any ideas? Assume for indirect proof. A, the conclusion is false. How would this help us?
By assuming it's false, that naturally raises the question of how, and then you answer the question how by saying there is no way how.
Say the last part again.
I said it in my head and it made sense a while ago, and now in words it's not really making sense. So you would say it's false because that raises the question, okay, why is it false? And then you answer that question right now with trying to prove why it's false, and then you show that you were incapable of doing that, and that proves it true.
Okay, good. Yeah, so that's exactly right. We assume that that the conclusion is false, and we try to see essentially what that would mean, right? How could it have been false? If these premises are true, is it even possible for this to be false? Right? Remember with validity, if these are true, then this has to be true, right? So if we assume this is false, and that somehow doesn't contradict the premises, then it's possible for it to be false, even if the premises are true, so it would be invalid, right? So the notion here is if this argument was really valid, if it was valid, then assuming premises are true and conclusion false would result in a contradiction. Remember when we did the truth tables? We didn't run indirect truth tables, did we? Did we? Well, one of the ways to do truth tables so you don't have to write it all out is you assume the conclusion is false and the premises are all true. Now, if that's possible, then it's not valid, right? The premises wouldn't guarantee the conclusion, even if they were all true. But this is basically the proof way of doing that. If if the argument was really valid, then if the premises were true, which whenever we do a proof, we're assuming they're true, right? Then an assumption that the conclusion was false will contradict the premises. It will generate a contradiction. So I assume that the conclusion is false. What would that allow me to do? Anybody see a rule I could use?
Use add to get A or B.
Okay, so I get A or B with 3 additions. What's that one right there?
C and B.
C and D. 1, 4 modus tollens. What's that allow me to do?
You can either get not C or
You can't get not
Are
C.
you-
You can get C.
You can get C, yeah. What else can you get from this?
D.
D. And let's just say for this one 5 simplification. What else can I get now?
You can also get not D.
Okay, now B. Contradiction, right? I close this out. Once I get my contradiction, I close it out, and I say that, well, not A must be true. Yeah, not A must be true, 3 through 8 indirect proof. So here's the reasoning. We know these are true. I assume the conclusion is false and the premises are true. Given that assumption is false, I end up getting an absurdity. Now, anything that entails a contradiction can't be true. Just axiomatically, right? Anything that entails a contradiction cannot be true. So if A entails a contradiction, it implies the contradiction, it can't be true, not A. Does that make sense? Well, but that's the conclusion, so I just proved the conclusion. But indirectly, not by giving you a direct step by step. Does that make sense? Okay. Now the other way to do this would have been to treat this as a conditional proof. Let's just say I made all these assumptions as a conditional proof. I assumed A, it got me B and not D, right? So I can say 9, I'll conjoin these, B and not B. 7, 8 conjunction. And then I can close this up by saying 10. If A was true, then a contradiction would follow. Right? Now you then have the law of non-contradiction, or LNC. What's the law of non-contradiction state? Anybody know?
I don't know, but I can take a pretty educated guess.
Yeah.
You
You
can't have
can't have, yeah, you can't have P and not P. That's all, yeah. If you want to put it modally, necessarily, this can't be true. There's no possible way that could be true. Well, if something of that form can't be true, this can't be true, right? So if I can consult this rule, and I can now say 11, I can just help myself to this. I can just say, you know what's true? What's true is that B and not B can't be true because of the law of non-contradiction. Well, I just negated the right-hand side, right? So what's that get me? Not A. And there's my conclusion. I proved it like that, right? Now, that's not in the book. But you can clearly use a law of non-contradiction like that. Does that make sense? Don't worry about it if you don't know what I just did, because you won't have to do that in the homework. But the point of doing that is to show you conditional proof and indirect proof are actually the same thing. They're just two different ways or procedures for writing the same reasoning process of making an assumption and deriving what that assumption entails, and then inspecting the results. Okay, so there you go. Those are the two techniques. Any questions? Time is it? 11:11, we got plenty of time. Let's practice some. Sound good? We'll stick with conditional proofs for now, and then if we have time, we'll get to indirect today as well. So let's do seven point 5.1. Okay, ready for numbers? I don't know which ones we already did. 4, 6, 8. Did we already do 8? I don't think we did. But if we did, don't do it. 9, 10. Yeah, okay. Let's work on these for a minute. See where we get, and then come up and do it. They haven't done yet. They're kind of doing, come on, let's figure that out in a minute. Samantha, are you done? Okay, cool. Yeah, let's, put one up. Who wants to go first? May I volunteer? Some of them?
Okay. By number
There's only
9.
one piece left. Actually, sorry, could you get within these lines right? Just for the camera. So everybody can see, do it well, and succeed.
So the first thing I'm going to do is I'm going to assume H.
Yes.
Yeah, I'm going to do that. And so then I get I, then N, using 4, 1 exponents. Yep. And then I can get I from that. Because of 3, 5, notice colons.
Good.
And so now I can close this conditional proof, and I can get H implies not I. With 4, 2, 6, not 6, conditional proof.
Yes.
So then I can get M or N. Using 7 to exponents. Yes. And then I can get the conclusion M using A3 Reductio system.
Nice, good job. Very concise, I like it. Good. Any questions on that one? All right, who's next? Come on up.
Do you want me to erase that one or just do it? assume J, you can get both of these with those points.
Yeah.
You can get not K and not M because 3 says not L.
Cool. Great.
And then you can join these together in conjunction. And then with the Morgans, you can get this
And then I
piece.
can do that. Good.
Or then you can get the answer.
Good. Great. Perfect. Very good. Very good. Good job. Now, we could have also done, we could have closed it at 9.
Oh, you
done-
could have?
Done the conditional, and then done De Morgan's within the condition. Does that make sense?
Yeah.
I mean, same exact number of steps and everything. But just in case anybody would have done it that way. All right, any questions on that one? Who's next? Come on up. Here he comes, coming down to do the proof.
For me, this whole thing just kind of feels cheap for the same reason that the addition rule feels cheap.
You gotta take what you can get, man. Sometimes reasoning gives you cool shortcuts.
I didn't quite hear because eraser, what'd you say?
You gotta take what you can get. Sometimes reasoning gives you nice little shortcuts for things.
It's not, well, that's the thing, it's not really taking what you can get at all, it's making exactly what you need.
Exactly. But if it makes logical sense in every step of the way, then you can, you've got this hypothetical reasoning structure.
So you, conveniently, I'm just gonna say that G happens to exist. I can make it down to either G or H.
Good.
Which,
Yeah. Nice.
and then,
Good, great, yeah, that's a great job. I would have done it in a longer way. So that's nice and concise, I like that. Cool. Something interesting to note is that this is how scientific theories are typically work. So when you have a scientific theory, before you confirm a theory, right, you have to first have your data. So you get data, like empirical data, observations, whether it be from a lab experiment, whether it be from, going observing how the natural world works, whatever. You have data, you come up with a theory. Do you know the theory is true just based on the data? Basically never. Because any amount of data, there's an infinite number of equally powerful theories that would explain the data. So a scientist is going to, whether that scientist be a hard scientist like the natural sciences, or a historian, or a psychologist or sociologist, or anything like that. You're going to have some data, you're going to come up with a theory. Now, how do you basically test the theory to show that it's true? Well, you do experiments and see if the theory holds up, right? Okay, but that's not really showing it's true. It's just showing that you haven't contradicted anything yet, right? It's just surviving you looking for contradictions through experiment. So how do you actually confirm that it's true? Well, one of the things you do is you take your data set, you take your theory, you assume your theory is true, and you say, what would follow from my theory? If all of the data is accurate, which, it's data, so we know, we observed it, it's accurate, and my theory was true, it would make all of these predictions. So if my theory is true, then given the data, C will be true. Now I do experiments, and I'm not just looking to contradict the theory, I'm looking, does it actually make successful predictions? Was C actually true? Does that make sense? Now the more successful predictions you have, that incrementally raises the probability of your theory, right? So the very structure of scientific hypothesizing and then confirmation has this sort of conditional hypothetical structure. That's why they call a theory, what else do they call a theory? An explanation, but also an educated guess, or a what? Hypothesis? Is that what you said?
Yeah, that's
Hypothesis is right.
how it is.
Yeah. Hypothesis. What's hypothesis? What's that mean?
Something that is hypothetical.
Yeah. Hypothetical. It's something that you don't exactly confirm, but it's an if-then, right? It's a, if this was true, then these predictions would happen, right? So the entire process of theory is just a process of coming up with hypotheses and testing them. Well, hypothetical reasoning is this, right? This is a model of deductive hypothetical reasoning. That's also why I think it's so important to teach it and not just brush past it, but, time constraints. Any questions? Okay.
Still, I haven't quite figured it out yet.
That's fine. Let's work on it together.
I can't figure out which is the right place to start.
Now think about, again, with all these rules, but also the techniques, you can make a bunch of assumptions and they don't lead anywhere. You're not wrong for making them. But yeah, back to the educated guess, part of hypothetical reasoning is you have this data, you're trying to get to some conclusion. The assumptions in a conditional proof are educated guesses about what might get you there, right? So even if you don't know where to start, starting somewhere is good. Trial and error.
didn't know where to go from here.
Yeah.
Or S and T.
Yeah, you can also get P.
That's what I'm going to see.
So what, yeah, so if you closed it right there, what would that give you?
It just says that it's possible for S and T to be true.
Yeah, so possible given what? So if you
Yeah.
did close it right there, it would be, what would you conclude from that conditional proof?
Given that P and R are true, then S or T. Or
Close, it would be, you could write it multiple ways, you could go, given that it's true that P would imply R, then it would also be true that T or S or S and T, whatever you want to write there. Is that gonna help us? I don't know.
Also, I tried to imply P, but then I just got Q or R.
Right.
What is it?
Yeah.
I'm just missing something here. I don't.
Well, I think it just might be the wrong, not the wrong assumption. You're not wrong. You just might need to make another assumption somewhere. So what I suggest doing is you close that one, and then you derive from it P then R, in parentheses, and then that whole thing would imply T. Does that make sense? Why? Like why that is a conclusion?
Yeah.
Okay. So now I think what you do, and I don't care how much board space this takes up, we'll just figure out another assumption to make, essentially, and see what we can get. What other assumption could we make? I mean, I guess we can make anything we want, right?
Yeah.
But,
So you can either make P or Q.
sure.
Try. And from P you can get.
Good.
I just need a way to get from P to R.
Yeah.
So
This is a tough one.
um,
Does anybody see ready to do it?
I really, that's what I really mean is P then Q. Because then if I get P then Q, I can get to these hypothetical syllogisms. Right.
Yeah, you could,
You're gonna
then you
get to
get
P
P
to
then
R.
R, right? Yeah, how can you get P then Q? I don't know if you can.
Would you want to do not Q, like assume not Q, because then that way on line 1 you could say, okay, P then R, and then that would give you line 2, which would go back to your first assumption and prove that right.
Yes, yeah. You could do it within the, do a conditional proof within the conditional proof, but it would get so complicated. And then you would end up still then just having a big string. But you're thinking the right way, for sure. Okay, so I guess that assumption didn't work out. At least so far. Does anybody see what we could do? I'm looking at the rules right now because I don't even see what we can do.
Yeah, I'm gonna go back and grab my book.
Yeah. Is this one written down correctly? P and Q are P and R.
So I'm going back into the trash. P and Q are P's and R's.
Oh, I'm thinking that, why am I thinking that's an I? Yeah, no, that's something. That's the P. P and R. That's the P. Conditional, constructive dilemma somewhere. Good. Oh man, this one's stumping me. Nothing? No one's got anything? What could we do? P then Q or R, that's gonna bug me all day. P then Q or R, Q then R, then S and P, Q then R, therefore P. Is it valid? Q then R, but if Q then R is true. Oh! So P gives me Q or R. Now, if it's true that P implies R, then S and P are both true. Now, I know on 3 that Q implies R. So, if P implies Q or R, if it implies Q, then if Q ends up being the one that's true, then I'm still going to get R. And if it implies R, then it's just going to be R. So either way on 1, P is going to end up implying R. Do you see how that works with 1 and 3?
Yeah.
So 1 and 3, somehow in there, if you combine those two, we don't have a rule for it, but if you figure out a way to use 1 and 3 together, you'll be able to eventually get P then R from it. Now 2, if you have P then R, then you have S and P, right?
So you're already there.
Right, so then you're already there. So how, though, do we use 1 and 3 to figure out how to get that to mean P would imply R? This is fun. I say we start, you already assume P there, right?
Yep.
Okay, so good. So that gets you Q or R. Now, given the assumption that P, we've got Q or R, I would put 11. Oh man, how do we do that? Watch it be like distribution or something, which is I loathe it.
We can't do distribution.
We need a way of showing that one of those, either one of those disjuncts on 10 would result in R. So P would get me Q or R. Let's see what's happening. P got me Q or R. I know we're about to run out of time, so if you need to leave, you're good to go. So I'm going to try to finish this before next class comes in. What if I did another conditional proof within one of them? I'm just going to assume for conditional proof the sequel, too. And then I go, well, let's assume that I have Q. See, if I assume that Q, well, then that would have gotten me R. Well, but I already know that. Let's say I assume that R. But a P would have implied R given something like, P then R then P. Anybody see it?
This may be wrong, but can you just get R from 2, like P to R since you have P? Or is that like stupid?
Wait, can't I get R from 2? What do you mean?
Yeah, cause it's like P to R,
Mhm.
I don't know.
Oh, right, so yeah, it would be P to R, but it's not actually saying that P implies R.
Yeah.
It's saying if it implied R, then this, yeah. So yeah, we couldn't do that. Okay, is there a rule that I'm just like having a brain fart over? How can we get this? Because you see the logic of what I'm saying? Either of these happening proves that P would imply R.
Is it possible to do like a not P or Q or R maybe? I don't know. And then move the parentheses?
Not P or
I don't think that would do anything though. I think you just end up in the same problem. You can't move.
Yeah, I think so too. I'll take that picture of this. I'm gonna solve it, and then next time we come to class, we're gonna do it. P, Q, or R. Shit. Is it something to do with, wait, Q or R, material implication on that. Not Q then R. Q then R, and not Q then R. Well, that means this is tautology, right? Not Q or Q. Can we see that? So continuing from here, I know 11, I have Q or R. I do material implication on that and turn it into a conditional. And it turns into not Q, then R, right? From pen, imp, or whatever it's abbreviated as. 12, now I can combine not Q then R and Q then R from 311 conjunction. What's that tautology? The tautology?
I told you, I thought they were both the same.
Man, there's really no rule for that, huh? But it makes, oh man, there should be a rule for this. I should just be able to say, not Q or Q. I should just be able to assert that at any point, right? Because it's tautology. So I'm just going to say it's a tautology. Well, then if that's the case, then I can do a constructive dilemma here from 1213, and it would give me R or R, right? And then I would end up, that would be R. And then that would, I could close that out, and then just say P implies R, right?
Yep.
And then I would get this, and then I would simplify it.
216.
But this isn't in the book, so I don't know how we solve it with the book's method. But does that make sense why you can just assert that? Okay. If you get that on a problem, that would be totally fine by me. I'd cheat too. Okay, that makes sense.
Yeah, somewhat.
I'm gonna still try to, we should try to figure out how this works for next time, with the book rule. All right, I'll see everybody later. Take it easy.